Welcome everyone. Today I'm going to talk about something which is very common in large language model context called vector embedding. What essentially it means. This means you're going to convert word, audio, video, images into some sort of number array. And what is the dimension, the element in the array? Um, it is decided based on the how many properties or attributes you want to capture in that. So typically, when we write something like a set of word, right? So let's say quick, brown, fox, and this. If you supply this as plain simple word as a word, it is not that effective in terms of finding the semantic meaning, finding the closeness with other similar kind of words. So for example, if I put black, yellow, red, they won't be able to match with the brown because there is no semantic connection, right? It just another word, and that's why it is not effective to use word as a word, rather convert it into an array which basically holds different characteristics. Now, take an example of how these characteristics can be defined. So if I go ahead and let's say take few type of characteristic, um, that is one characteristic, and then you have that royalty, and then you have got food. So, and then if I supply my large language model while I'm giving the training, couple of word, let's say I supply king, queen, and then I supply apple. Now, if you see here, let me point them to, king has got both royalty and masculinity. Queen has that royalty, and then let's say the apple is the food. So based on the strong attribute closeness, it will be categorized or grouped. Now, in a typical vector space, where if you imagine a 3D vector space, you have got this kind of grouping available for the words. So certain food will come together, so certain royalty will come together, certain vehicle type will come together. So that's how they're kind of grouped all together. Now, how this array conversion really happens in all practicality. So when you train a large language model, right, with huge amount of data, then it looks into these data, and then it uses a neural net is used here. So, and then during the training, model looks at millions of examples, literally millions of examples, and then see how each of these data points basically relate to one another. So whatever colors it finds, it probably group them all together, and then it learns, maybe let's say take an example, coffee or tea could be often in a similar context. Let's say somebody says that I drink a cup of, and then it could be tea, coffee. So they basically looks similar. It becomes similar, right? So it's kind of that way from the examples given, right? So um, why this is useful? Because you think of like going into an e-commerce portal and trying to search a word called shoe, but the whole website has identified all its footwear as footwear. So if you do an exact search, right, it won't match and it won't give you the result back, which is not efficient. So instead, it will, if you search with a shoe, even if there is no entry, it will find footwear because semantically they mean the same. They are very close to each other, right? They're actually the same one. Now that's how the vector databases, right, keep them close to each other and then make it like quickly available and find you an alternate option even if you're not providing the the thing. Common use cases of using that outside of LLM is search engine, right? And then you have got recommendation engine. So when you listen to specific type of song in a audio player, you tend to get the similar vibe music. It's if you listen lot of romantic music, you tend to get a lot of romantic music references coming to your list. That's the recommendation engine. In the large language space, we use retrieval augmented generation, where we supply our own data to the LLM, which is not in the LLM's memory, to fetch the relevant information. So we vectorize that relevant data because large language model understand LLM. So the large language model understand the vector embedding. So we first convert them into vector embedding, convert the query, which is the prompt in the vector embedding, match and bring the chunk which are relevant and then give it. So that's how the RAG works. So these vector embedding becomes essential in these kind of use cases. Now, let me do a little bit of math. So just to not to overwhelm, but to just to have an idea. So if you go back to the fundamental high school mathematics of, let's say I draw another line and I draw join. Okay. Now if I have this is 90-degree and this is your hypotenuse. If we consider this as a base, and this is the perpendicular, and this is the angle, let's say theta. Now the cos theta is base by hypotenuse. Sine theta is perpendicular, and tan is sine by cos. So we all know that. So this is just a thing, right? Now, if you have also studied the vector in the high school mathematics, you know the vector has a starting point and a direction and a magnitude. So if you have this noted as vector A, this will become like this. If you have another vector which is a bit bigger, the magnitude is more, direction is different, starting point is different. We can start another vector from here with a smaller magnitude but different direction of C. So this is how you think of them as different sizes matchsticks, right? If you have used matchsticks, you know one side there is a black portion where you just lit the fire. So you basically consider them as matchsticks in lying across different sizes. Size is the magnitude, that's the length, but the direction is something like that. All right. Now, when we convert these words into a vector array, right, they become list of such values, right? And in typical vector databases, when embedding happens, they normalize it because when we try to find the similarity of the two words, the semantic meaning of two words, we don't, let's say, in the if you refer this diagram, if you have to, if you have two vectors, one is here, maybe this way, and another is here, maybe that way. Okay. If you have to measure the distance of this distance, you don't measure the Euclidean distance, that is Cartesian distance. We don't do that. We don't do that. What do? We do something called cosine distance, cosine similarity, basically, we call it. And the formula of the cosine similarity is that if you consider this as vector A and this as vector B, is the dot product of vector A and vector B and the magnitude of vector A into magnitude of vector B. When, as I said, like when we put these into vector databases, they normalize it. So if we normalize it, we put them as a one, that is unit vector, and then it becomes the dot product of the two. So we ignore the magnitude. So this is the magnitude. The denominator is the multiplier of the magnitude. So ignore the magnitude. And just to give you why we ignore the magnitude is that, take an example of a 500 page PDF of cloud computing. And you have a 50-word LinkedIn post on Azure. When you send these two chunks, right, they are similar. But the magnitude of this 500-page document is so large that if you start considering the magnitude, don't normalize it, it will be too far away, too far dissimilar from this article of Azure. So that's the reason why we kind of try to ignore the magnitude part. That is basically handled by the thing. Now, just to understand the cosine similarity, there are certain numbers which you get, right? So it typically between -1, let me put a different color, typically -1 to 1. Now, the cosine similarity is generally between 0 to 1, right? Which means that 0 is where it is the same. Sorry, 1 is where it is the same. 0, it is too far. This is far. This is close. Now, let me explain you why. Why we consider 0 as close. But if you consider the Euclidean geometry, right? Typically cos theta equals to 1 when theta is 0 degree. That means if you consider these two lines and this is theta, when it is 0, that means it merges the same line. It becomes the same line here, and then it is the same. So if there are two vectors, this is the same, right? So that is why it is close. It is the same. If you say cos theta equal to 0 when theta is 90 degree, that means you have one vector which is going here, and the angle of these two vector is 90 degree. They are too far away because their direction is not the same. We're considering direction, not the thing. So it's too far. So that is why it is too far. And anything which is 180, that means the next vector becomes something like this here. That is your 180 degree. Then it is minus 1. So cos theta is minus 1 when it is 180 degree. Just to visualize that why it is something like that, we can also go back to the primary uh, geometrical representation of these coordinates in form of a cos and sine. So if you consider this graph, okay, mathematical graph, and then if I draw a triangle, hopefully it will become a good triangle. Yes, and then I kind of, let me just draw a better one. So first draw the triangle. Yes, and then I draw this line. This is x-axis, this is y-axis, and then if I give this 0 point and we take the 1 unit, so we go x-axis 1, so this is x-axis, this is y-axis, we go x-axis 1, and then we stay 0 in the y-axis, so this is 1 0. If we go stay in the 0 of the x-axis, go into this 1 of the y-axis, it becomes 0 1. And then if we go to the negative side of the x-axis, then it becomes minus 1 0. In typical coordinate, you identify these numbers as cos theta, sine theta. Okay, so cos is the x, sine is the y coordinates. Now, if you have a vector, let me put a different color. If you have a vector going towards this direction, if you have a vector, let's just draw something like this. Going to this direction, you have another vector going to this direction. This is the theta we are talking about. Now, when it is 0 degree, that means the next vector, which is this vector, is kind of matching. All right. If we have, let's say, try to draw that very close to each other so that we can differentiate them. So this is 0 degree. So there is no, I assume that they are the same. So that is 0 degree. Then your cos theta becomes 1. That is the logic which we discussed earlier, right? So 0 degree, that means same, becomes 1. So when the cosine similarity gives you the number 1, that means they are same. If you search uh, a curly brown hair or a quick brown fox, if you type brown and it finds the brown, 2 brown will give you the same vector representation. So they are the same. Okay, so that's why it is. Now it is, if it is 90 degree, let's put a different color. Let's say this one. If it is this one, let's say 90-degree, little side, and then what happens? Your cos theta becomes 0. So that's why cos theta is 0, not 0. So cos theta is 0. Just identify 0, not O. And then when it is 180-degree, that means this is the angle and your vector is somewhere here, opposite direction. You get -1 for the cos theta position. So that is why it is -1 when theta is 180-degree. So that's how typically we have learned so far how this can be done, right? Now, one of the benefits of using this cosine similarity is that it can find the semantic meaning, but you may also like to do the keyword search in your database. So we prefer vector search. That means we first do the keyword search to match if the keyword matching is happening, and then we have that semantic search, that is vector search, and group them together and bring the value from there. So you basically have this formula here for the cosine similarity. So if you say cosine similarity, and then you have that vector A dot product of vector A, vector B, and you have magnitude of vector A, vector B. So that's the kind of formula we apply. And it's just normalize that, make it 1, 1, and then it becomes like a. So the vector databases like Azure AI Search, Redis, Postgres, they basically do normalize by themselves. So it is built into that capability. And the dimension we use is 1536. The embedding model available from OpenAI has got the availability. Now, one thing you need to remember, if you are vectorizing some text with one um, model, you have to vectorize your prompt to the same model. Otherwise, that they will not be able to match because the way the algorithm changes, right? Uh, the single dimension, if you just convert it into a single dimension array, does not actually tell you the full story. Huh? So you will not find, even if that dimension is smaller, let's say 10 dimension, um, if you type cloud computing and software engineering, um, it can't differentiate because it does not have too much of. So if you have cloud computing and software engineering, you don't be able to differentiate these two, right? Because there are very few characteristics available. When you bring in too many dimension, that too many characteristics, right? That also becomes like large in the sense of takes too much of memory, takes time to compute. So the sweet spot, based on the research, the researcher has come up is 1536, the number. And let us just see some of the examples here on how this vectorization really works. So let me show you. Now let's see some demo here. Let me show you the embedding. Now what I'm gonna also show you is how I'm using the GitHub model. Now if I take you to the GitHub, so you say GitHub marketplace. If you go to the marketplace of the GitHub, and if you just open that, you have got many models available, and you can see that the list of models are added. There are many models available. You can use it for free. And I search embedding. I'm using this OpenAI text embedding 3, which is the model which is now used here. So, and you can use this without any subscription. So GitHub is free. You basically go ahead and do that. Let me show you the how I initialize this. Hmm, how I initialize this. So I'm using this OpenAI SDK, the library. And then I'm also using this models.github.ai inference, so which are where the model is running. And then I need to supply this personalized GitHub token, which you can create from GitHub and just apply it here. Typically, you load it from the environment variable, but you can just, for the demo purpose, you can host it over here. And then I'm gonna just initialize the client with the base URL and the key. And the model name is this for LLM and this for embedding. So I just mentioned the embedding model name, and this is the text embedding of OpenAI. That's how you call the GitHub model. Now, beauty of this is that you are not restricted. You are still be able to run things. So you can kind of like try these things. The exact same code, if you just copy, paste in your environment, it will run. Okay. So you don't have to really think too much about whether I have got a subscription. Can I still do that? Now, let me show you the embedding code which I have written. It's a small piece of code where I kind of have this line. A quick brown fox jumps over the lazy dog, and this will convert into a vector array of dimension how much? 1536. That's the dimension. Okay. So I will go to this embedding, run this piece of code. I can run it in my bisware. So I'll say UV run 02 embedding. Now this is gonna run this thing, and you can see the dimension is 1536 because I'm doing a length of this embedding array which is getting generated, and then my input is just A. So I'll show you, change this input into the text input, and then you will see that. Let me also show you the input here. Print, what is the actual text? So the text input, dimension, embedding, because embedding is a bit too large, so it'll occupy a lot of spaces. So we'll just put them into the end of our message. And you can see that the dimension is 1536, the text is this, and you see this is the array which got generated, right? It's a huge array of 1536 element. So let me clear it up, and then let me change it to something like a single word. So if I just say vector and run this code, it's gonna do the embedding for the word vector, just the single word vector, still the same size array. Different representation, but the same size array. The array size remains the same. So the uniformity is here. So when you supply a paragraph versus a single word, your array size will be the same. Okay, so that's why data chunking strategy is important, and there are tools available to identify the data chunk, the similarity, the overlap, based on which they, if you're reading 500-page PDF, you may want to chunk it because you don't want to do the vectorization of all the 500 pages together. So you want to do, let's say, each paragraph or each section or each chapter, depending on what the chunking strategy looks like, and little bit of overlap here and there, so that you can kind of have a connectivity or map between these two chunking, right? So this is how the vector looks like when you kind of generate them with each other. So you can do vector search between two vector. So if I say the first one, that is quick brown fox jumps over the lazy dog, uh, this one versus blue, you will find the similarity is close to uh, 0, which means I'm pretty close, right? Almost similar. If you search with something absolutely different, let's say William Shakespeare, then you may not find the similarity that close, right? It'll be clo closer towards 1 because it is a bit far away. You hardly will find anything which is negative. Sometimes, yes, you do, but a negative means like it's kind of -1 means 180-degree. Anything negative means more than 90-degree, right? So it's two vector can be more than 90-degree from each other if you start calculating the angle between them. So that's how this basically looks like that. A little bit of math, a little bit of understanding how it internally works probably will help you think, uh, design, and decide when you build using this vector embedding, because this is a fundamental understanding. Though we're not doing this embedding by ourselves, there's already model and algorithm available. But if we know what exactly is happening behind the scene, we can probably uh, plan well, design well, make the better experience for our end user. Hence, I just thought of spending a little time here.